Now we're going to talk about the other important number that characterizes a linear transformation, which is the trace. So if I have some matrix with these entries on the diagonal, and there are going to be a bunch of other stuff in this matrix too. The trace is just the sum of whatever is on the diagonal. So we're doing a sum. We should use summation notation for that. And I'm going to write a sub I. I have a repeated index. That means I need to sum over this index. So I'm going to sum from where this is 1 to where this is n implicitly. I means the row and the column are the same. This has to be on the main diagonal. We're going to add all those entries together. So I told you, but didn't prove for you, that the determinant is invariant under a change of basis. No matter what coordinates you use, no matter how you rotate or change your coordinates, you're always going to get the same determinant. That's true of the trace as well, and I'm going to prove that for you. It's a very good exercise with index notation. So when I do a change of basis, that means I go from A to R times A times R inverse from the earlier formula I gave you for a change of basis. Now, if I take the trace of both sides, that is A sub I. There's an implicit sum right here. And we would like that to be the case for what the trace of this is. So I'm going to take R inverse and take the I entry of that. Now, if you did the earlier exercise about proving how matrix multiplication works in index notation, we're going to use that to fill in about how we can write this matrix multiplication in index notation. If you didn't do that, then the key result is that if A is equal to BC, then A sub IJ, let me do that in blue. This is going to be your outermost entry of the matrix. This is going to be your innermost of all the indices. So that's BC sub IJ. And when I break this down, the outermost index goes right here. The innermost index goes on the far end of C. And in between, we do matrix multiplication over these entries. We do row times column. And we're going to repeat that right here. So my outermost index better be I. Then I have A. Then I have R inverse. My innermost needs to be I. And now I can start filling in the middle with how I matrix multiply these together. So R gets multiplied to A. That means the second index on R is the same as the first index on A. A gets multiplied to R inverse. That means the second index on A is the same as the first on R inverse. Now, the nice thing about getting to here is that now that I've put indices on all of these are just numbers. They're not matrices any longer. These are matrices. These are when I need to think about rules about how matrix multiplication doesn't commute. Now, there is an implicit summation symbol, actually two summation symbols, over J and over K, over all of this. And that summation is doing all the matrix work for us. That's where the matrixy stuff lives. All of these individual entries tell me a specific number in the matrix. Now, these are just numbers, and numbers just commute. So now that all of these things just commute, I'm going to move R inverse to the front. So I've got R inverse of Ki, and I have R of I j, and I have the original A of j k. Now right here, I notice that the second index of R inverse is the same as the first index of R. I can do matrix multiplication right here. So now I've got these two multiplied together to R inverse R, K j times A of j k. R inverse R, that's just the identity matrix. So this becomes identity matrix K j times original A times j k. So the j's are repeated. I am multiplying A times the identity matrix, and we all know what that is. It's just A. And the leftover indices are K, K. And look, this tells me to sum over when the row and the column are the same from 1 to n. This is exactly the same as the trace. I used a different index to describe the trace, but that's totally fine. At this point, when the index is repeated, it doesn't matter. It doesn't matter if I call it I, j, k, or z, or aleph, or whatever. It's still going to cover 1 through n, just like this did. So the trace is invariant under a change of basis. So when you're studying some complex problem and trying to wrap your hands around some weird linear transformation, what you want to focus on are the trace and the det. And we're going to keep using these properties to tease apart rules for special operators and special matrices. And when our operators start transcending matrices, these are still going to be important.